My name is Satoshi Takizawa. Came from Japan, and my profession is water supply engineer. So I thought for the first time I'm the only engineer from Japan, but I was wrong. I was not the only one. But my slide, my pictures that I'm going to show you seems to be a little bit different from what I have seen before my presentation. So let me briefly introduce the issues that we face in Japan and in other countries. I came here for the first time to see the Black Sea. It's a very, very beautiful, wonderful sea. But we also have a sea here. The picture I have taken in the southernmost island of Okinawa. It's a small island, but with 1 million population, plus 5 million tourists from all over the country. So the beach is not only for swimming. When we go out for swimming, we want to take a shower, we want to drink beer and water, then we need more water. So the beach is not only for swimming, but here you can see this is a seawater desalination plant we built about 15 years back. Until that time, they had a very, very difficult time to get clean water. After we built this seawater desalination plant, they have enough water. But this is not only the case in Okinawa, in California, in Australia, in many parts of the world, they are facing the difficulty in getting clean water. So let me briefly outline the water supply systems and the issues we're now trying to deal with. So when I travel around the world, I quite often see these kind of photos and pictures. So I visited Hanoi in Vietnam. I visit this city usually once or twice in a year. And the city is expanding so fast. People is just coming in from the rural regions to the city. And city population is growing so fast, and the city mayor need to get the water to supply to the city. So they built a huge water aqueducts, water transmission lines, but because they want to save the money to build that one, they built 6 years, they built this 6 years ago. This is a 2.4 meters, very big water transmission mains. But within 6 years, they had water pipe leakage 8 times. So they are facing water supply, very difficult situation in this kind of cities. This is not only the case in Hanoi city. Many Asian cities are facing quite a similar kind of water shortage. Right? Then the people need to get water. So what they do here is, you can see this one. This is not electric power cable. This is their water supply systems hooked onto the power cable. So we have to see carefully which one is power cable and which one is water supply systems. So what they do here is they put the PVC pipe attached with small pumps, and they suck the water from nearby ponds, and they send the water via this kind of tubes to their households. So each household do this kind of things. So you can see here, they call it something like a spaghetti type water supply systems. Because they have to do that, because they cannot wait until the city fix all these kind of engineering problems. So this is a situation they face in many cities, big cities. So water, we need water for our life, but we have to be aware where it comes from. Water, we take a part of natural water cycle systems. So we have to understand carefully what is the natural water cycle systems. So we need a science to better understand natural water cycle systems. We should not too much have an influence to the natural water cycle systems. We have to be very modest to take what amount of water we can take from natural water systems and streams. But we are again facing the other kind of problems. Because the natural water cycles is gradually changing. Many scientists say that it's partly because of climate change. And climate change impact is especially severe in developing countries, including Africa. This is a picture of the cereal production damages, a percentage reduction of the future cereal, like corns, wheat production, how much production will be decreased in some part of Africa. So brown one is more than 50% reduction of their cereals. So it's very, very difficult for the future in these countries. So I visited one of so-called sub-Saharan country, which is called Burkina Faso. And I saw here, this is the only big tree I can find. So no rain means not only people cannot get water, they cannot get fuels, you see. Because if you don't have any rain, no plants, no trees, so they don't have their fuels. Okay? So it's very, very difficult for them to get the water. So what they do is, this is a villages, very typical villages in Burkina Faso. So the ladies, housewives, ladies, they have to walk distances, sometimes a few kilometers to get water. And this one is about 20 liter, means 20 kilo. So she's got 2 bottles, it's 40 kilograms, and they have to carry back the water, back into their house. And sometimes they use bicycles to get the water back to their house. But this lady, 1, 2, 3, 4, 5, 6, 7, 8 bottles. So they have to use a cart with donkey. But their family size, I have to say, their family size is very, very large. On the average, they have 20 to 24 members in a household. So you can calculate simply how much water they have to carry back to their house every day. So it's a big challenge. And according to this publication, it was published in PLOS Medicine back in 2010, there's a linkage between the amount of the water supply and the infant mortality rates. This one x-axis is the total number of population in percentage unserved population, means people without access to pipe water. So from 0 to 80%, and this one is infant mortality rates. So if a country, this is a country-wise data set, and if a country has a high rate of unserved population, the infant mortality rate in general is higher. So this is a general linkage between the infant mortality and total number of unserved population. And these bubbles, large bubbles means large country with higher population, and the yellow one is low-income country, and red one is high-income country. So you can see from the picture, these bubbles, mostly yellow ones, means the low-income countries suffering still the low rates of water supply service and high rates of population infant mortality rates. So when we go see the villages, we always ask as a water engineers, we have to figure out what we can do. So we ask, can we take water sample? And this lady is a master of this well. She sort of dominates and she say okay or not okay. So she said that okay, he's a translator. So I requested for a sample. And she said okay, but you have to take the sample yourself. I will not help, you have to take your sample. It was a kind of difficult, but finally I was happy I get a sample. Okay, but you see, this is just 2 liters. And they have to bring back these bottles, 20 bottles per day. So how many times they have to do this? So it's a big challenge. And on top of that, I put the water into a cup, plastic cup, and you can see inside, it's filled with dirt. And they have to bring back this water to their households, and then they have to figure out whether they can drink directly from this, or they can do something to make it better. Okay? So usually, we can find some sort of methods to clean the water. This is very famous, live straw, but they can drink just a small amount of water. And this is also ceramic pot filter. So made in Burkina Faso, they can produce this kind of ceramic pot. You can see no hole. It's not a flower pot. If it's a flower pot, you need a hole here. No, you cannot use your flower pot. So no hole. But this is not good enough to separate E. coli and viruses. The spore is so large, so that all germs and E. coli just pass through. And this one is solar disinfection system, so it's good, but when it's cloudy, they cannot get clean water. So these are the challenges they face. So we brought some instrument from Japan to Burkina Faso. This one is a membrane filter, ceramic membrane filter manufactured by a Japanese company, and it's very good. And these are the photos of water. This is what we call low water, the water we just take out from the well. It's a bit dirty. And this is a filtered water, it's clean. So he's my driver, and he's a bit thirsty, helping us getting water, and he requested this water. So I said, okay, you can take it. And he's very happy to get it. And this one is so-called, we have to wash the membrane filters. We call backwashing, putting the pressure from the other side and clean the membranes. And this one is backwash water. So this filter retains those turbidity and also some E. coli. So this is good, but seems like this one is a bit expensive for the local people. This one is very easy. Just pick up the water, but 2 meters high, and this pressure, it's about 2 meters difference. It's good enough to get the water in a bucket. So we thought this one is good for them, but they said this one is a bit too expensive for them. So then we have to figure out what we can do again. So these kind of small water treatment systems, as you know, is becoming more and more popular because municipalities are lacking sort of financial and technical resources to supply enough water. So the people, they have to do themselves to get the water, clean water. So these are the rooftop tanks in Vietnam, and they have a variety of ceramic filters to clean the water. But in cities, they have quite an advanced water supply or water cleaning systems just under the sink in your kitchen. So this is equipped with activated charcoal, adsorption, ion exchange, UV, and reverse osmosis membranes. It's a very advanced ones. But they want to buy this and equip with their drinking water. It's a bit expensive, but they like it. And this one is households, very typical in Vietnam. So we can tell that they have a sand filter here. You know why? The wall is lead. This is lead because the groundwater contains iron, and sometimes they don't clean the filter. So there's an overflow of iron-containing groundwater. So their wall becomes brown. So you can tell which households have sand filter. So all this, they try to get clean water. One of the problems in many countries in these days is a very trace amount of toxic substances, including arsenic. In Vietnam also, in the groundwater, they have a high concentration of arsenic, and the people are worried about it. And that's why they try to buy household water treatment kits. But this is our results of water treatment using sand filter, a very simple sand filter, and this one is reverse osmosis membrane filters. So arsenic usually have inorganic arsenic has arsenic-3, arsenate, and arsenites and arsenates, and this is total arsenic, and this is arsenate. So it seems like with sand filter, it is good to remove the arsenate, AS3, with more than 90%, 90 to 90%, 99% removal. But this total arsenic removal is a bit low, less than 90%. And with reverse osmosis membrane, it is opposite. The total arsenic removal is between 90% and 99%, and arsenic-free removal is less than 90%. So we suggest that a combination of these two processes may produce arsenic-free or very low amount of arsenic for them to be. So this is a situation they're facing. But the only problem with this system is recovery rate is very low, because reverse osmosis membrane can produce only 20% of the water which is passing through the reverse osmosis membranes. That means 80% is gone. It's just waste. So my student from Vietnam calculated what will be the future if every household equipped with membrane systems, reverse osmosis membrane, how much percentage of water demand in the future in Hanoi City will increase. Well, that is a lot. So this is good in terms of arsenic removal, but it's not good for the water conservation and water management. So again, we have to figure out alternative systems. So we, as a water engineer, in the past are facing different kind of contaminants. Long time ago, we just tried to remove from water, like grit, sand, like that, protozoates and bacteria. But nowadays, we have to get rid of small ones, like viruses, and some colloids and organics, and disinfection byproducts. We disinfect water with chlorine and other oxidants. Then we produce some very small amounts of disinfection byproducts. So we have to remove those. And sometimes ions. So this is a big challenge, because to supply water to a small community, we have to supply at least 1,000 meter cube of water for a small community. But when it comes to a big city like Balna, we have to produce a large amount of water, like 1 million meter cube per day. That is a huge amount of water. But we have to target these small things. So there's a big gap between sort of analytical chemistry levels of contaminants and engineering application of any kind of methodology. So there's a big gap between these two. But to do that, in the past, we employed several kind of systems. The most easy is gravity sedimentation systems. Just put the contaminant in the water, leave it for a few hours to a day, and then the grit will gradually settle down. The second is when it comes to a little bit small ones, we have to put some chemicals, we call chemical coagulation processes, combined with some membrane or sand filtration systems. And then when it comes further smaller ones, or some bacteria and viruses, this is not good enough. So we have to add some disinfectants into the water. And then we have other ways to put the oxidants to degrade those contaminants. And also we have some absorption processes like activated charcoal. All these are chemically intensive, and we have to put a lot of energy. So then we have to figure out what to do with that. According to the report of U.S. Environmental Protection Agency in the United States, about 3% of the whole energy is to be used to supply and treat the water to the cities in the U.S. So we have to deal with this high energy demand. So with that all background, we saw that exclusion zones model will be the future of our water treatment processes, because it requires very, almost no energy. Okay? So it's a big challenge, because this is just, it's more than 1,000 times greater than the molecules, but still a few hundred microns. But we have to produce this amount of water. So it's a big challenge for us as an engineer. With that background, I would like to report to you a couple of results that we published recently. And maybe it is not necessary to explain what is the exclusion zone phenomenon. This is one example. This is a naphthalene membrane, and this is colloidal particle. And after some minutes, we can see a clear water zone here. So we measured the size and the rate of formation. So the size gradually increases up to 300 seconds or 5 minutes, and then stabilize. We monitor this one up to 15 minutes or 900 seconds. So it's almost stabilized, no change, up to 15 minutes. But this is a few hundred microns, and we want to make it larger scale, a little bit larger. Even if a household scale, it's too small scale. So these are the conventional systems like chemical coagulation, filtration, and energy-intensive membrane filtration systems. So forget about these. We try to focus on how we can make use of exclusion zone phenomenon. So Professor Pollack already reported one very interesting systems with syringes. And the goodness of this exclusion zone application is particle and pathogen removal without chemicals and external energy, very small energy. And no byproducts, of course there's no oxidation processes, so no byproducts, and it's very simple. Okay, it looks very good, but we still have a challenge. The water productivity is still very low in this system. Water production rate is reported to be 2 milliliters per hour, and recovery rate is still not quite high. So then we have to figure out how to improve this low productivity. The ideas are good, but as an engineer, we have to improve the productivity. So I discussed with my students, with my researchers. I discussed for 3 hours, then we found after 3 hours, something's happened here. Okay, this is naphthalene membranes. We can see our exclusion zone very close to the naphthalene membranes microsphere. So this one is a bit large and it gradually settles by gravity. So we found the difference between the gravity settling and this one is with naphthalene. So the difference we define as the effect of, we call it phase separation, with clear water phase and particle phase. So pH is gradually getting down after this phase separation. So because this happened only after we put the naphthalene membrane piece into the water, we estimated there will be linkage between the exclusion zone and phase separation. So we monitored, we measured the development of EZ and the top supernatant layer. So these circles indicates EZ growth. So in the past we monitored only 15 minutes and then okay, stop, the next experiment. But that time we discussed for a long time and we forgot about our experiment for 3 hours. Then we found that we have to wait for 3 hours to see what's really going on there. So we monitor, it's going up, 15 minutes, oh, stabilized, stop it. But we continue. Then we found it's gradually coming down to nearly 0. Then the supernatant size is gradually growing up. So this one is the whole supernatant, but this one is gravity settling. So we calculated the difference to be the cause of phase separation. So this blue triangle is the net supernatant size. It's gradually going up, whereas the EZ size is going down. And this monitoring further encouraged us to think about the linkage between EZ and phase separation. Then we took close-up pictures, how the phase separation to be take place. This is about 3 minutes, nothing happens. 10 minutes, we can see some water here. 30 minutes, the water is here. And 40 minutes, you can see clearly, very clear water. And if we add some salts, sodium chloride with 0.5 molar concentration, it's high concentration, so that we can prevent EZ formation. In these cases, we cannot see any ones. But without salts, we can see EZ and phase separation. So we saw that EZ is the cause of this phase separation. And this picture, you can see very clearly, the EZ water is just around here, Nafion membrane. It's gradually floating up to formulate this clear water on top of that. So the basic mechanism we found is EZ water firstly formed, and it floats up. And why it floats up to the top? It's the next question we have to get an answer. Floating up, maybe it's because of the density difference, buoyancy force, it's going up. That's what we saw. So what we did is we changed the concentration of particles, in this case carbon black. This black part is carbon black. So we changed the concentration from low concentration to high concentration. I'm sorry, this is not the highest, but these are the differences. So you can see the lowest ones, we cannot clearly see the EZ, but when the concentration is gradually going up, we can see a clear water zone here. So the rate of formation is a bit different. 0.48 is this one. It's no clear supernatant. But when the concentration is increased, we can see a clear water zones. So it is dependent on the particle concentration that we found. And then we increase further, expecting the efficiency should be better. But to our surprise, when we increase the concentration, this is a concentration in log scale, we further increase the concentration. When the concentration is too high, again, we didn't see this phase separation. So phase separation takes place in a certain range of particle concentration, particle depth. So this, I think, is one of the reasons why in the past nobody reported these findings. Because this is, I have to go fast. Because this is dependent on the Nafion membranes, so we increase the number of Nafion membranes in this cuvette from 1 sheet to 4 sheets. We found the first rate is fast with 4 membranes, but the terminal, final supernatant size was not so much different. And then we tried to figure out why the number of the Nafion sheet didn't affect the final terminal supernatant size. One reason is Nafion area gradually declined and EZ formation rate dropped. This one is 4 membranes. Nafion area is first about 4 times different, but gradually, because the particles gradually settle down, the area that faced with the Nafion is gradually coming down. So that's one reason. The other is with 4 Nafion membranes. This one is highly concentrated. So we saw these are 2 reasons why we cannot find this clear water zone. So far we used only Nafion membranes, and then we saw what's going to happen with other membranes. So we used Nafion membranes, mixed cellulose acetate membranes, regenerated cellulose membranes, and cellulose acetate membrane. With all these membranes, we can see a clear water zone. So, but we can find the largest clear water zone with Nafion membranes. That's what we found. Then this is a bit difficult to explain, but we used different types of particles, same diameter with different surface functional groups. We used two different particles with amino carboxylate and sulfate groups surface functionalized. The average EZ size almost the same, but the supernatant size was very much different, with amino acid largest and sulfate the smallest. We have no answer to why this happened, but I would like to draw your attention to this. Right. One reason we can explain the reason why this happened is with amino acid functional group, the particle we observe aggregation from 0.23 microns to 1.96 microns. Then we calculated the gravity settling rate as 0.36 millimeter per hour. but the difference between these two is much greater than this rate. So there should be something else we don't know that can cause a difference between different particles. Effect of high ionic strength. This is again very tricky. Okay. First, we can see a clear water zone here, but after waiting for 3 hours, this result is very difficult to explain. With no salt, we can see clear water zone. With 1 mM, we can see, but at 5, we cannot see any. And then it comes down. And with 5 hours, we can see a very clear zone. And then we found the salt also is rejected at a rate of about 60%. Let me go through very quickly about the application of this process. We tried how we can apply our findings to a sort of water treatment equipment. It's very simple. This is a inflow with pumping systems with miniature of tubes. And this is a picture. Then we can find a clear water zone. Then we use particles, black particles, and then we found that the removal rate is 99.98%. The recovery rate is very high. And the removal rate is nearly 99%, nearly 100%, and the recovery is almost 100% of the water was recovered. Then we changed the flow rate. Even if we increase the flow rate to 5 times, we can maintain high recovery rates of water. So this is a challenge we are facing now. It's the picture, and what we did is we just moved maybe 10 times towards this way, but we have to move further to get water treatment processes. Okay? With that, I would like to thank you.
Thank you very much. We've reached the time, but maybe we can have one more question. If there is one interesting question.
I don't know if it's an interesting question, but it's a question. So next to the naphthalon, you have an exclusion zone. Beyond the exclusion zone, you have protons. And I wonder whether it's the protons that are the missing factor in explaining some of this, because those protons will then link all of the microspheres and whatever to form big complexes which then might settle to the bottom. Do you think that's a possibility?
That could be. So far, we just came up with this result, and we didn't look carefully into the mechanisms. So we look.
Okay, one more question in the back.
So when you add salt, it lowers the effect. So does that kind of make it difficult to use as a desalination device?
We hope so, but the salt rejection rate is still 60%, which is not high enough to supply fresh water.
Yeah, but you could recycle that. But
that's a good idea.
But it seemed like when you added salt, the effect went away.
Yeah.
Is that right, or did I misunderstand that?
The
exclusion zone got smaller when you added higher concentrations of salt.
If the salt concentration is beyond certain level, up to some levels, it's fine. So we cannot so far apply seawater desalination.
But
the salt level is too high.
You had 10,000 parts per million.
Yes.
It worked, but above that it started.
Yes.
Okay, thank you very much for your interesting presentation.